On May 18th, 2026, one atmospheric wave caused 5 separate weather emergencies across an entire continent. At the same moment, Wyoming was under a blizzard warning. Boston was melting under record heat. A tornado outbreak was active. So was an extreme wildfire risk. And flash floods were ripping through the middle. One wave, 5 disasters. One day, 2 months earlier, Earth recorded a 217-degree temperature gap between 2 points on the same planet at the same time. We are going to cover all of it: the wave, the gap, the physics behind the floods, and what scientists are saying they cannot predict anymore. If you find this valuable, subscribe so you don't miss what comes next. Let's go. On May 18th, 2026, the atmosphere did something that had never been recorded in the entire history of weather tracking. A single wave of air, stretching thousands of miles across, triggered 5 separate weather emergencies on one continent in one day. A blizzard in Wyoming, a record heat dome pressing down on the East Coast, a tornado outbreak tearing through the middle of the country, extreme fire weather burning across the West, and a flash flood emergency active at the same time. 5 categories, 1 wave, 24 hours. The National Weather Service issued 404 active weather alerts that day. 404. To put that in scale, imagine every major city from New York to Los Angeles getting a different emergency warning on the same afternoon. That is roughly what the map looked like. Meteorologists watching the data called it a total failure of normal seasonal weather. Spring was supposed to be spring. Instead, the country got winter, summer, and everything violent in between, all layered on top of each other at once. The wave responsible has a name. Scientists call it a Rossby wave, and understanding what went wrong with it is the key to understanding everything that followed. A Rossby wave is an enormous, slow-moving bend in the air currents high above the planet. Picture the air at 30,000 feet as a river, a wide, fast-moving river that circles the entire globe. Under normal conditions, that river flows in smooth, gentle curves. Those curves determine where cold air sits and where warm air builds. They are the reason Denver gets snow while Miami gets sunshine. But on May 18th, the river stopped moving forward. It stalled. The curves locked into place like a frozen roller coaster. Cold air stayed pinned over Wyoming. Scorching air sat parked over New England, and the systems trapped underneath each bend had nowhere to go. They intensified, they deepened, and they started producing extremes that the historical record had never seen stacked together like that. Here is what made it worse. Temperatures at the altitude where weather forecasters track air pressure reached 2 to 3 standard deviations above the climate record for that date. Standard deviations are how scientists measure how far outside normal something is. 1 standard deviation is unusual, 2 is rare, 3 means the data your models are built on no longer applies. Forecasters were essentially flying blind. Scientists confirmed this event. The National Weather Service documented every alert. Meteorologists on the ground watched it unfold in real time and described it as something outside the range of known atmospheric behavior. The question that immediately followed was simple. Was this a once-in-a-century accident? Or was something structural changing in the atmosphere that made this kind of day more likely? The answer points towards something that had been building for years. The Rossby wave did not stall randomly. Something had weakened the atmospheric current that normally keeps it moving. Something had changed the balance of heat between the Arctic and the equator, and that change had been accelerating quietly, in numbers most people never see, for the past decade. Before we get to what caused the wave to break down, you need to understand what a healthy Rossby wave actually looks like, because what happened on May 18th only makes sense once you see how far the system had drifted from normal. And the answer to that is more visual than you'd expect. Every single day of your life, your weather was decided miles above your head. At around 30,000 feet, higher than any commercial airplane cruises. At full altitude, a river of air circles the entire northern hemisphere. It moves at speeds up to 250 miles per hour. It stretches for tens of thousands of miles, and it never stops. This is the jet stream, and it is the reason some cities get snow while others get sun, why some summers cook and some stay mild, why storms roll in from the west and rain falls where it does. The jet stream is the single most powerful driver of day-to-day weather across the entire continent. Rossby waves are the bends inside that river. They form naturally because the Earth rotates and because the planet's surface is uneven. Mountain ranges, ocean temperatures, and land masses all push and pull on the jet stream as it flows overhead. Those pushes create the giant S-shaped curves that you can see on any weather map showing upper-level winds. A healthy jet stream moves fast and stays tight. Its bends are moderate. The wave pattern drifts slowly eastward, which means no single weather system gets stuck in one place for too long. Cold air visits, then moves on. Rain falls, then clears out. Think of it like a spinning garden hose. When the water pressure is strong, the stream stays straight and tight. When the pressure drops, the hose starts to wobble. The bends get wider and slower. Water sprays in unpredictable directions. When the jet stream weakens, it does exactly that. The bends in the Rossby waves grow deeper and wider. They slow down. Sometimes they stop entirely. That stalling is the key to everything. When a Rossby wave stalls over a region, it acts like a lid. Cold air trapped under one bend of the wave cannot escape north. Heat trapped under the next bend cannot move east. Weather systems that would normally pass through in 2 or 3 days instead sit in place for a week or more. Snowstorms intensify. Heat waves deepen. Rain events pile up rain on top of rain. Scientists confirmed this is exactly what happened on May 18th. The wave stalled over North America and held 5 simultaneous extreme systems in place, like a hand pressing down on a table. What drives the strength of the jet stream in the first place? Temperature difference. The jet stream gets its energy from the gap between cold polar air and warm tropical air. The bigger the gap, the faster the river flows. The faster the river flows, the tighter and more stable the Rossby waves stay. Now, here is where the story starts to shift. That temperature difference, the gap that powers the whole system, is shrinking. The Arctic is warming at a rate 4 times faster than the rest of the planet. Cold polar air is less cold than it used to be. The gap between polar air and tropical air is closing. A weaker gap produces a weaker jet stream. A weaker jet stream produces slower, deeper Rossby wave bends. And slower, deeper bends produces more stalling. More stalling produces more days like May 18th. This is confirmed science. Researchers have been tracking the weakening of the polar temperature gradient for years. What happens to the weather when that weakening accelerates? The next chapter answers that. And the numbers are harder to picture than you might expect. The Arctic is supposed to be cold, brutally, reliably, permanently cold. That coldness is not just a feature of the far north, it is the engine that keeps weather patterns stable across the entire planet. The Arctic is warming at 4 times the rate of the rest of Earth. Scientists call this Arctic amplification, and it is confirmed by decades of satellite data, weather station records, and ocean temperature readings. The Arctic is warming faster than anywhere else, and that acceleration is changing the rules of atmospheric physics. Here is why the speed matters. The jet stream runs on temperature difference. It is powered by the massive contrast between freezing polar air and warm tropical air. That contrast creates pressure differences in the atmosphere, and those pressure differences spin up the winds that form the jet stream. The greater the contrast, the stronger and faster the jet stream flows. When the Arctic warms faster than the tropics, that contrast shrinks. The engine gets less fuel, the jet stream slows down, and a slow jet stream is an unstable jet stream. Picture a river running downhill over a steep slope. Fast water stays in its channel. It moves forward, it carries everything with it, and it stays relatively straight. Now flatten the slope. The water slows. It starts to wander. It carves out big loops and bends. It pools in places. It takes a long time to get anywhere. That is the jet stream right now. The slope has flattened. The river is wandering. The deeper bends and slower movement mean weather systems stay locked in place much longer. A heat dome that would have lasted 4 days now lasts 10. A storm that would have dumped 2 inches of rain now parks over a city and drops 8. A cold air outbreak that would have swept through in a weekend now sits for 2 weeks. Scientists confirmed that the Arctic has lost more than 2/3 of its summer sea ice volume since the 1980s. That ice loss directly reduces the cooling effect of the polar region. Less ice means more open ocean. Open ocean absorbs sunlight instead of reflecting it. More absorbed sunlight means more Arctic warming. More Arctic warming means less temperature contrast. Less contrast means a weaker jet stream. Every step in that chain is confirmed. The debate among scientists is about exactly how much of the recent jet stream behavior can be directly linked to Arctic warming versus natural variability. That part remains an open question, but the physical mechanism itself is solid. What makes this chapter of the story unsettling is the feedback inside it. Arctic warming weakens the jet stream. A weaker jet stream allows more heat to build up in mid-latitude regions, which sends more warm air toward the poles, which warms the Arctic further, which weakens the jet stream more. The loop feeds itself. And here is what that looked like in practice. While the jet stream was weakening over months and years, the atmosphere was quietly loading up a second problem, one that had nothing to do with wind patterns and everything to do with water. The warmer the atmosphere gets, the more moisture it can hold. And the amount of extra moisture the air has absorbed in the last decade goes far beyond what most people picture when they think about humidity. The scale of it changes how floods happen, how storms form, and how fast rain falls. That mechanism is coming, but first, you need to see exactly what a broken jet stream looks like from the ground. On the morning of May 18th, 2026, a weather forecaster in Wyoming was issuing blizzard warnings. That same morning, a forecaster in Boston was telling residents to expect temperatures that would break the all-time record for that date. Both of those things were true at the same time, on the same continent, on the same Tuesday. Wyoming sits in the Rocky Mountain West. Boston sits on the New England coast. The two cities are roughly 2,000 miles apart. On a normal spring day, they might have different weather, but the idea that one would be buried under a blizzard while the other was cooking under a record heat dome on the exact same day falls so far outside normal ranges that meteorologists struggled to find historical comparisons. The stalled Rossby wave was responsible. One deep bend in the wave had pushed a massive cold air mass down from Canada and locked it over the northern Rockies. Wyoming sat directly under that frozen bend. The next bend in the wave, curving back the other direction, had pulled warm air up from the south and trapped it over New England. Boston sat under that heat dome like a pot with a lid on it. The wave was not moving. So neither bend moved. And the systems under each bend just kept intensifying. In Wyoming, temperatures dropped fast enough to freeze standing water. Snow piled up in areas that had been seeing normal spring conditions the week before. In Boston, temperatures climbed to levels that matched the hottest summer days on record in a month that typically stays cool. 2,000 miles apart, opposite seasons, identical calendar date. Meteorologists watching the upper-level wind data confirmed the wave structure causing it. They could see the exact bends in the jet stream on their maps. They understood the mechanism. What they had no framework for was the intensity, the combination, and the fact that this was happening simultaneously with 3 other extreme events across the same continent. Because while Wyoming was snowing and Boston was baking, the atmosphere was also producing a tornado outbreak in the Central Plains, an extreme wildfire weather alert in the west, and a flash flood emergency somewhere in between. All of it at once, all driven by the same stalled wave system. What that split-screen moment illustrated was something beyond a bad weather day. A healthy atmosphere distributes extremes across time. You get a heat wave one week, then it breaks. You get a storm, then it clears. The system moves. The jet stream carries everything forward. A stalled wave collapses that distribution. Every extreme arrives at once, concentrated into the same window, because the atmospheric conveyor belt has stopped. Scientists noted that the simultaneous occurrence of 5 categorical weather extremes in a single 24-hour period had no clear operational precedent in the historical record. Confirmed, the record books had nothing to match it to. The 404 weather alerts issued that day stretched every forecasting system the National Weather Service operates. Staff across dozens of regional offices were issuing alerts for events that had never been mapped alongside each other. But here is the thing: the wave did not appear overnight. The conditions that allowed it to stall that severely had been building for months. One of those conditions was a temperature reading taken in March of that same year, a number so extreme that atmospheric scientists are still working through what it means. It involved a gap of 217 degrees on a single planet. The National Weather Service runs on a simple system. Forecasters observe the atmosphere, identify developing threats, and issue alerts when lives are at risk. Watches, warnings, advisories. The system was built to handle one region dealing with one major threat at a time, maybe 2 overlapping events during a severe season. On May 18, 2026, 404 active alerts were running simultaneously across the United States. Confirmed. To understand what that number means, you have to understand what each alert requires. Every single one is written by a human forecaster. Each one describes a specific geographic zone, a specific threat type, a specific instructions for the public. Each one has to be monitored and updated as conditions change. Forecasters issue alerts, track their own alerts, coordinate with neighboring offices, and update emergency management agencies in real time. 404 running at the same time means 404 separate emergencies unfolding simultaneously. The coverage zone for each alert represents hundreds of square miles of land and hundreds of thousands of people. The 5 categories of extremes active that day covered radically different threats. A moderate-risk tornado outbreak means supercell thunderstorms capable of producing violent, long-track tornadoes. An extreme fire weather alert means conditions so dry, so windy, and so hot that any spark could produce a fire that moves faster than a person can run. A flash flood warning means water is rising faster than roads can drain. A blizzard warning means zero visibility and life-threatening cold. A record heat dome means temperatures high enough to kill vulnerable people within hours of outdoor exposure. These 5 threat types require completely different emergency responses. Tornado protocols send people underground. Flash flood protocols send people to high ground. Heat protocols send people indoors. Fire protocols send people out of entire regions entirely. Blizzard protocols keep people from driving at all. Issuing all 5 simultaneously across one country means emergency managers in neighboring counties are giving opposite instructions to their residents at the same time. The operational complexity alone was extraordinary. What made it scientifically significant was the cause. Every one of those 404 alerts traced back to a single atmospheric structure. One stalled Rossby wave, one malfunctioning bend in the jet stream. The alerts looked like 5 separate events. Meteorologically, they were one event with 5 faces. Climate scientists noted that multi-hazard events of this type had been increasing in frequency. A single weather driver producing cascading simultaneous extremes across distant regions is a pattern that older climate models struggle to reproduce, because those models were built on historical data that did not include events like this. The models were calibrated to a different atmosphere, Scientists confirmed that no single-day event matching this combination of alert types and geographic spread appeared in the operational weather record. The word unprecedented got used carefully because meteorologists are trained to be precise. But the event qualified, and what followed in the days after May 18th was a period of analysis that raised an even larger question. The wave behaved the way it did because the atmosphere surrounding it had already changed. The temperature patterns feeding that wave were themselves records, including a temperature gap measured 2 months earlier that still does not have a clear explanation in standard models. That gap is the next piece of this story, and the numbers in it are going to take a moment to picture. A tornado needs moisture. It needs warm, unstable air rising fast from the surface, colliding with cold, dry air descending from above. It is a violent mixing event. A wildfire needs the opposite. It needs dry air, low humidity, strong winds, and heat. Moisture kills a fire. The same moisture that fuels a tornado would shut a wildfire down before it started. These two events should never appear on the same weather map at the same time. The atmospheric conditions that create one actively prevent the other. On May 18th, they were both active simultaneously across different regions of the same continent. Confirmed. This is one of the clearest illustrations of what a stalled Rossby wave actually does to a continent's weather. The wave does not create uniform conditions. It creates radically different conditions locked in place across different regions. Under one bend, the atmosphere was loaded with Gulf moisture, warm and unstable, spinning up the ingredients for tornadoes. Hundreds of miles away, under a different bend, the atmosphere was bone dry, hot, and running at wind speeds that would fan any ignition source into a catastrophic fire. The Central Plains saw the tornado threat. The National Weather Service issued a moderate risk for that region, meaning forecasters believed supercell thunderstorms capable of producing significant, potentially violent tornadoes were likely. A moderate risk from the Storm Prediction Center is serious. It covers situations where trained storm spotters are activated, where school systems begin early dismissal, where emergency managers pre-position rescue teams. Simultaneously, the western region was under an extreme fire weather alert. Extreme is the highest tier on the fire weather scale. Red flag warnings had been active for days. Fuels on the ground were critically dry. Wind events were forecast to push sustained speeds that could drive a fire front faster than emergency vehicles could reposition. Two threat systems, opposite atmospheric needs. Same 24-hour window. The meteorologists who documented this noted something specific. The boundary between the tornado threat zone and the fire weather zone was sharper than normal. Usually, weather systems bleed into each other at the edges. There is a transition zone where conditions shift gradually. On May 18th, the transition was abrupt. The stalled wave structure had pinned each air mass into its own region so firmly that the boundary between them was almost like a wall. Scientists tagged this as a signature of an unusually strong and stationary wave pattern, confirmed. The wave was not just slow, it had nearly stopped. What that means for forecasting is significant. A moving wave distributes its effects across time and geography. A stationary wave concentrates them. Regions under the tornado sector stayed there for an extended period. Regions under the fire weather sector stayed under it too. Communities on both sides had to sustain emergency protocols for far longer than a moving system would require. The operational and human cost of extended simultaneous emergencies is compounding. Resources stretched across tornado response and fire suppression at the same time leave less capacity for either. And that was only 2 of the 5 extremes running that day. The number that put all 5 of them in context came from 2 months before May 18th. A temperature reading taken in March 2026 that described a split inside the planet itself, a split that measured 217 degrees from one end to the other. In March of 2026, Earth held 2 temperatures at the same time that should not coexist on a single planet. At Vostok Station in Antarctica, the temperature dropped to -105 degrees Fahrenheit. That is a number that is hard to picture. At that temperature, exposed skin freezes in under a minute. Jet fuel thickens. Metal becomes brittle. The air itself carries so little heat that breathing it unprotected would damage your lungs. During that same week, parts of the United States recorded surface temperatures surging past 112 degrees Fahrenheit. Pavement hot enough to burn skin on contact. Temperatures that push the human body toward heat stroke within an hour of outdoor exposure. The gap between those two readings was 217 degrees Fahrenheit on the same planet. Atmospheric scientists confirmed this measurement. The data came from weather stations and satellite readings that track surface and near-surface temperatures globally. The gap itself is what drew attention. Scientists noted it as evidence of severe structural changes in the way the planet distributes heat. Here is what that means. The atmosphere has one primary job beyond everything else. It moves heat from the equator toward the poles. Warm air rises near the equator, flows towards higher latitudes, releases its heat, and sinks back. That cycle is the planetary thermostat. It has kept temperature differences across Earth within a range that life depends on. When that cycle works properly, the poles are cold and the tropics are warm, but the difference stays within a predictable band. Extreme readings happen, but they are isolated, short-lived, and separated by vast distance. A 217-degree simultaneous gap suggests the planetary thermostat is struggling. The atmosphere is failing to redistribute heat evenly between the cold end and the warm end of the planet. Cold is getting colder in some places. Hot is getting hotter in others. The range is expanding. Scientists noted this gap as consistent with the broader pattern of atmospheric polarization, driven by an accelerating thermal imbalance. That is a theory, an explanation that fits the data, but has not yet been confirmed as the definitive cause. What is confirmed is the temperature readings themselves and the fact that the gap exceeded anything in the recent record. The practical consequence of that gap is invisible but enormous. Every large-scale wind system on the planet runs on temperature differences. Ocean currents, storm tracks, monsoon patterns, hurricane formation zones, all of it depends on the temperature gradient between warm and cold regions being within a certain range. When that gradient stretches beyond the range the systems were calibrated to, weather patterns start to behave in ways the models cannot predict. Scientists do not yet know how the 217-degree gap affected deep ocean currents. That impact remains undocumented, an unknown. What is known is that the March gap and the May event are part of the same story. The atmosphere over North America stalled on May 18th because the thermal balance powering its wind systems had already been destabilized months before. One piece of that destabilization lives at the bottom of the Earth, in one of the coldest, most remote places humans have ever built a research station. Vostok Station sits nearly at the center of Antarctica. It is 11,400 feet above sea level, perched on a flat sheet of ice 2 miles thick. The nearest coast is over 800 miles away. The nearest inhabited city is thousands of miles distant. There is no road to Vostok. The only way in or out is by aircraft, and aircraft can only land there during a narrow window in the Antarctic summer, when temperatures rise just enough to make the conditions survivable. The Russian scientists who staff Vostok Station work in the most extreme cold environment on land that humans have ever occupied continuously. The record low temperature ever recorded anywhere on Earth was set at Vostok, -128 degrees Fahrenheit. In March of 2026, Vostok recorded -105 degrees Fahrenheit during the same week that temperatures in parts of the American West pushed past 112. That reading placed Vostok well within its extreme cold range, consistent with the deep Antarctic winter pattern that governs the station year-round. The significance of the reading was not the number itself. Antarctic winter temperatures at Vostok are expected to be extreme. The significance was the contrast. The gap between Vostok and the simultaneously measured heat in the United States revealed something about the state of the global atmosphere at that moment in March. Scientists who track planetary heat distribution flagged the gap as a data point, showing the atmosphere was failing to smooth out temperature differences across latitudes. The system that normally blends cold polar air with warmer mid-latitude air was working poorly. Cold was staying colder than expected in the south. Heat was staying hotter than expected in the north. Vostok also matters for a different reason. Beneath that 2-mile thick ice sheet, one of the largest liquid water lakes on the planet sits sealed in total darkness. Scientists call it Lake Vostok. It has been isolated from the surface for an estimated 15 million years. The lake holds clues about how life survives in extreme isolation and what ancient atmospheric conditions looked like before modern industrial activity. Ice cores drilled near Vostok have given scientists some of the most detailed records of Earth's past climate that exist anywhere. Those cores capture ancient air bubbles, trapping samples of the atmosphere from hundreds of thousands of years ago. By analyzing those bubbles, scientists can measure how much carbon dioxide and methane existed in ancient atmospheres and what temperatures followed. The data from those cores confirmed something important. The current level of carbon dioxide in the atmosphere is higher than at any point in at least 800,000 years of recorded history in the ice. The rate of increase is faster than any period the ice cores captured. That rate of increase is what the next chapters are about. The gases building up in the atmosphere are not just warming the surface, they are fundamentally changing how much moisture the air can hold, and that change in moisture is the mechanism behind the floods, the storms, and the escalating rainfall events that are now breaking records worldwide. Vostok sits at the cold extreme of what happened in March. Understanding what was happening at the warm extreme, and inside the oceans feeding that warmth, requires a different kind of number. A number that starts with 90%. On May 18th, temperatures at a specific altitude above southern New England reached 2 to 3 standard deviations above the operational climate record for that date. Confirmed. Meteorologists watching that number go up described it as the moment they understood the event was outside normal parameters. Standard deviation is a tool scientists use to measure how far something is from average. It is precise. Every dataset has a center, the average, and a spread how far values typically fall from that center. One standard deviation covers about 68% of all normal outcomes. 2 standard deviations covers about 95%. 3 standard deviations covers 99.7%. When something lands 3 standard deviations above the record, it means that outcome falls in the outermost fraction of a percent of everything the historical data ever captured. Every temperature reading, every measurement taken at that altitude and location, going back to the beginning of the record, that reading sat outside nearly all of it. The practical meaning for a forecaster is serious. Climate models are built on historical data. They use past behavior to predict future behavior. When current conditions consistently land beyond the edge of that historical data, the model's predictions stop being reliable. The model was calibrated for a range of conditions it is no longer seeing. Think of it this way. Imagine your school has kept height records for every student who ever attended, going back 100 years. The tallest student in that entire record was 6 feet 4. Now a student walks in who is 7 feet 2. Your height tracking system, your charts, your averages, your percentile ranges, they still work fine. They just no longer describe this student with any accuracy. You are measuring someone the system was never built to measure. That is what happened to the atmospheric models on May 18th. The temperature reading at altitude did not just break the daily record, it broke it by a margin wide enough to step outside the statistical framework the models use to generate predictions. This is why scientists described the forecasting challenge that day as operating without a reliable map. The instruments still worked. The readings were accurate, the models simply did not have a framework to tell forecasters what would happen next, because nothing in the data record matched what they were already seeing. This is confirmed. Meteorologists documented the deviation clearly in their analysis of the event. The gap between what the model expected and what the atmosphere produced was measurable and significant. 3 standard deviations above the record is a signal that the record itself may no longer be the right measuring tool. If extreme events consistently land beyond the edge of the historical range, then the range needs to be recalibrated. Scientists are actively working on that recalibration. But the data needed to build a new baseline is still accumulating because the events generating it are happening now. The forces pushing the atmosphere beyond these thresholds have been building for more than a decade. One of the most powerful of those forces operates not in the air, but underwater. 90% of all the extra heat trapped by rising greenhouse gases has gone into one place. And that place is about to release it. Every time you have ever heard that the planet is warming, most of that warming was happening somewhere you could not see or feel, down in the ocean. The World Meteorological Organization confirmed it. 90% of the excess heat building up in Earth's climate system is being absorbed by the oceans. Confirmed. The ocean is not a passive body of water sitting beneath the atmosphere. It is an active thermal storage system, absorbing the vast majority of the extra energy the planet is accumulating every single day. To understand the scale, consider this. The oceans cover 70% of Earth's surface. Their average depth is about 2.5 miles. The volume of water sitting on this planet is so enormous that it takes decades to heat up noticeably. That slow absorption rate is actually what has protected surface life from feeling the full force of atmospheric warming much sooner. But that protection has a cost. The heat stored in the ocean does not disappear. It sits there, accumulating year after year, and it interacts with the atmosphere above it in ways that directly drive the weather events you experience on land. Warm ocean water evaporates faster. That evaporation loads the atmosphere with moisture. More moisture means heavier rainfall when storms form. Warm ocean water also provides the energy source for tropical storms and hurricanes. The warmer the water, the more energy available for a storm to pull from the surface. A hurricane crossing water that is 2 degrees warmer than the historical average does not just get slightly stronger, it can intensify dramatically, doubling in wind speed in a matter of hours. The World Meteorological Organization reported in early 2026 that Earth was more out of balance than at any point in observed history. Confirmed. Incoming solar energy was arriving faster than outgoing energy was leaving the planet. The gap between what comes in and what escapes back to space is growing. Every year that imbalance continues, more energy enters the ocean stores it, and eventually that stored energy comes back up into the atmosphere, gradually through evaporation, suddenly through storms. Ocean heat content in 2025 reached record levels. Scientists confirmed this through a global network of sensors called Argo floats, thousands of robotic instruments drifting through the ocean at different depths, measuring temperature and salinity continuously. The Argo data made the pattern clear. The ocean was warming not just at the surface, but thousands of feet down. Deep ocean warming matters because surface cooling events, like an unusually cold winter or a period of strong winds, can only affect the top layers. The heat stored hundreds of feet below the surface is unreachable by those short-term events. It stays locked in, stable, accumulating over years. The practical effect is a climate system that cannot cool itself down quickly. Even if greenhouse gas emissions stopped completely today, the heat already stored in the ocean would continue warming the atmosphere for decades. The system has momentum. That momentum is now expressing itself in a very specific way in the atmosphere above the oceans, in the rate at which the air is absorbing water. And that rate, tied to a precise physical law, is the reason floods are changing in ways that infrastructure was never built to handle. The Atlantic Ocean is not the same body of water it was 20 years ago. Ocean temperature data confirmed that large sections of the Atlantic, including the Gulf of Mexico and the tropical Atlantic, have been running at consistently elevated temperatures over the past several years. In some years, surface temperatures in the Gulf of Mexico reached levels more typical of late summer during months that historically stayed cooler. Confirmed. This matters for a specific reason. The Gulf of Mexico is the primary moisture source for weather systems that move across the central and eastern United States. When a low-pressure system drags air northward from the Gulf, the moisture content of that air determines how much rain falls, how intense thunderstorms become, and how long precipitation events last. A warmer Gulf loads that air with more water. When that wetter air then collides with cold air masses or gets forced up by terrain, it dumps more rainfall in a shorter period than weather infrastructure was designed to handle. Storm drains, rivers, levees, and culverts were all built based on historical precipitation rates. When rain falls faster and heavier than the historical rates, the infrastructure fails. The process driving this is straightforward. Water evaporates faster from a warmer surface. The warm Gulf acts like a humidifier running at maximum power. Every storm system that passes over it picks up more moisture than it would have picked up from a cooler surface. That extra moisture travels inland and eventually falls. But the Gulf is only part of the system. The Atlantic's warming also affects the temperature gradient between the ocean surface and the air above it. That gradient drives the wind patterns over the ocean, which in turn steer hurricanes and tropical systems. A warmer ocean with a different temperature profile can redirect storm tracks, potentially sending systems toward coastlines that historically saw fewer direct hits. Scientists also confirmed that ocean heat content affects the depth of warm water available to tropical storms. Hurricanes weaken when they churn up cold water from below the surface. In deeper warm layers, that cold upwelling is reduced, allowing storms to maintain or increase their intensity longer. In 2025, several Atlantic storm systems showed rapid intensification patterns, meaning they gained significant strength in very short windows of time, at rates that historical models assigned low probability. Confirmed. Forecasters found these rapid jumps harder to predict because the conditions enabling them went beyond what older predictive tools were designed for. The ocean heat engine is not a future threat. It is an active present system driving current weather outcomes. The moisture it pumps into the atmosphere connects directly to the physics of rainfall, the weight of storms, and the speed at which flood events develop. That physics operates through a law you have probably never heard of, but have certainly felt every time a massive rainstorm drenched your city faster than the storm drains could handle. And it starts with a 7% number that changes everything about how rain works. For every 1.8 degrees Fahrenheit that the atmosphere warms, it holds 7% more water vapor. Confirmed. This is not a guess or a model projection. It is a physical law called the Clausius-Clapeyron relation, and it describes a fundamental property of how air and water interact. 7% sounds small. It is enormous. The atmosphere currently holds more moisture than it did 50 years ago. The warming that has occurred since then, roughly 2.5 degrees Fahrenheit above the mid-20th century average for much of the globe, means the air is carrying significantly more water vapor than historical precipitation records were built around. That extra water has to come down somewhere, and when it does, it comes down fast. Rain does not fall in a gentle, evenly distributed drizzle because the atmosphere planned it that way. Rain falls when air rises, cools, and can no longer hold the water vapor it was carrying. The rate of rainfall at any given moment depends on how much moisture the air is carrying and how fast it is being forced to release it. More moisture in the air means more water available to release during any given storm. The same storm system, traveling over the same geography, with the same wind speeds and the same pressure gradient, will now drop more rain than it would have dropped decades ago. The storm has not gotten stronger. The air has just gotten wetter. Scientists who track extreme rainfall events confirmed that heavy rain events have become 10 to 40% heavier in recent decades due to climate-driven moisture increases. confirmed. The World Weather Attribution Group analyzed multiple extreme rain events globally and found this pattern repeating consistently. This is why a storm that would have dropped 2 inches of rain in the 1980s now drops 3 inches, and 3 inches in 6 hours overwhelms drainage systems that were designed to handle 2 inches. A 30% increase in rainfall does not produce a 30% increase in flooding. It can produce flooding where there was no flooding before, because the system tips past a threshold it was never designed to cross. The flash flood warning that was part of the May 18th 5 alert day was not a coincidence, alongside the other events. A stalled Rossby wave had locked a moisture-loaded air mass in place over a region. The warm Gulf moisture feeding that system carried more water than historical flash flood models anticipated, and the result was rainfall rates that exceeded the capacity of the ground and the drainage infrastructure to absorb. Repeat this pattern across enough storm events and enough geographic regions, and you produce a new baseline for what flooding looks like. Infrastructure built for a drier atmosphere starts failing more often, in more places, with less warning. Cities are already living with this. Some of the most dramatic examples came from places where almost no one expected catastrophic flooding. One of those places is a desert city that got swallowed by water from an atmosphere that simply could not hold what it had absorbed any longer. Dubai is a desert city. Average annual rainfall there is about 3.7 inches. For comparison, Los Angeles gets about 15 inches per year. Phoenix gets about 8. Dubai, sitting on the edge of the Arabian Peninsula, with almost no natural vegetation and almost no drainage infrastructure, was built to handle almost no rain. In April of 2024, 17 months before the May 18th event in North America, Dubai received a year and a half worth of rain in a single day. In roughly 12 hours, the city recorded more than 6 inches of rainfall, confirmed. The results were immediate and total. Water covered highways to the level of car doors. The international airport, one of the busiest in the world, flooded across its runways and terminals. Stranded aircraft sat in standing water. Thousands of vehicles were abandoned on submerged roads. Residents trapped in apartments and homes had no drainage system to rely on because the city was never built with one capable of handling that kind of event. The atmospheric cause was confirmed. A slow-moving storm system pulled moisture from the warm Arabian Sea and the Persian Gulf, both running at elevated temperatures, and dropped a volume of water that the region's historical climate record had never produced. The moisture-loading effect of warmer sea surfaces directly contributed to the event's intensity. Scientists from the World Weather Attribution Group analyzed the Dubai flooding and confirmed that climate change made an event of that intensity significantly more likely. The Arabian Sea has been warming, increasing the amount of moisture available to storm systems that form over it or draw from it. Dubai had no framework for the event because its entire infrastructure was designed around its historical climate. 3 to 4 inches of rain per year spread across occasional light showers. The engineering assumptions behind every road, every building, every airport terminal were calibrated to that baseline. When the atmosphere produced an event that sat entirely outside that baseline, the infrastructure had no response. Water pooled with no place to go. Drainage channels designed for light events overflowed within minutes. This is the core problem the 7% rule creates at the infrastructure scale. Cities, bridges, highways, and storm systems are all designed using historical rainfall data. Engineers use what is called a 100-year flood standard, meaning they build to survive a flood that has historically happened about once per century. Climate scientists confirmed that events meeting the old 100-year flood threshold are now occurring more frequently in many regions, as the moisture content of the atmosphere has increased beyond what older infrastructure calculations assumed. Dubai was an extreme case because the gap between historical conditions and current atmospheric behavior was so wide, but the underlying mechanism, warmer oceans loading more moisture into the air, delivering that moisture faster during storm events, is active globally. What makes the moisture story even more significant is that water vapor is not just a passenger in the warming atmosphere. It is an active participant in making the warming worse. Water vapor is itself a greenhouse gas, and the warming it contributes to causes the air to hold even more water vapor. That loop is the next part of this story, and it is one of the most powerful amplifiers in the entire climate system. Most people know carbon dioxide as the main greenhouse gas driving climate change. Confirmed, it is a major driver. But carbon dioxide alone does not account for the full scale of warming the atmosphere is experiencing. Water vapor is the most abundant greenhouse gas in the atmosphere. Confirmed. It traps more heat than any other single gas in the system. And unlike carbon dioxide, which accumulates slowly over decades as emissions build up, water vapor responds almost instantly to temperature changes. Here is how the loop works. Carbon dioxide enters the atmosphere from burning fossil fuels. It traps heat. That trapped heat raises surface temperature slightly. Warmer surfaces cause more water to evaporate from oceans, lakes, and land. More evaporation puts more water vapor into the air. Water vapor traps additional heat beyond what the carbon dioxide alone was trapping. That extra heat raises temperatures further, causing more evaporation, which adds more water vapor, which traps more heat. Scientists confirmed that this water vapor feedback roughly triples the initial warming caused by carbon dioxide alone. Confirmed. Without the water vapor amplification, the warming effect of doubled carbon dioxide in the atmosphere would be roughly 1.8 degrees Fahrenheit. With the water vapor feedback included, that number climbs to between 4 and 5 degrees Fahrenheit. The same atmosphere that is producing heavier rainfall and bigger floods is simultaneously amplifying the warming that is driving those events. The water is doing two jobs at once, falling as catastrophic rain during storms, rising as invisible vapor that traps more heat between events. This feedback is self-reinforcing. A warmer atmosphere holds more water vapor. More water vapor warms the atmosphere further. The system does not need any additional carbon dioxide input to keep pushing temperatures higher once the vapor feedback kicks in fully. The carbon dioxide sets the process in motion. Water vapor carries it forward. What limits the feedback is complex atmospheric physics involving cloud formation, altitude, and the distribution of moisture across different layers of the atmosphere. The exact sensitivity of the climate system to water vapor feedback is one of the most researched questions in atmospheric science. The range of estimates has narrowed over decades of study, and the confirmed middle estimate points toward that roughly tripling effect. This also means that the amount of warming already locked into the system is larger than the carbon dioxide concentration alone would suggest. The extra heat being stored in the oceans, confirmed at record levels in 2025, will continue evaporating water into the atmosphere for decades, sustaining the vapor feedback even as surface conditions change. The Arctic atmosphere, scientists confirmed, is becoming increasingly moist as polar temperatures rise. That extra Arctic moisture is accelerating ice melt because moist air holds and transfers heat more effectively than dry air, which leads back to reduced ice cover, which leads back to a warmer Arctic, which weakens the jet stream. Every thread in this story connects to every other thread, and the gas that set all of it in motion is still rising. Carbon dioxide concentrations reached an all-time recorded high in 2024. The increase that year was the single largest year-on-year jump in the measurement record, and it did not arrive alone. The measurement station at Mauna Loa in Hawaii has been tracking atmospheric carbon dioxide continuously since 1958. That record is one of the longest and most precise in climate science. Every year, the number goes up. Every year, scientists update the charts. In 2024, the carbon dioxide concentration in the atmosphere reached its highest level ever recorded in that dataset. Confirmed. The World Meteorological Organization reported it. The number also stood higher than at any point in the ice core record going back 800,000 years, confirmed through the kind of ancient air bubble analysis done near the Vostok ice sheet. Carbon dioxide is a greenhouse gas. When sunlight hits Earth's surface, the surface radiates heat back upward. Carbon dioxide in the atmosphere intercepts that heat, absorbing it instead of letting it escape into space. The more carbon dioxide in the air, the more heat gets intercepted. The increase in 2024 was the largest single-year jump in the recorded measurement history, confirmed by the World Meteorological Organization. The rate of increase, meaning how fast the concentration is climbing year by year, has been accelerating for decades. The total amount of carbon dioxide now far exceeds anything the planet has seen since before humans existed. The global average surface temperature in 2025 reached 2.57 degrees Fahrenheit above the 1850 baseline. Confirmed. The 1850 baseline represents pre-industrial conditions before large-scale fossil fuel combustion began driving greenhouse gas levels upward. 2.57 degrees Fahrenheit above that baseline means the planet has already warmed significantly beyond the conditions in which all of human civilization developed. To picture the scale of 2.57 degrees, consider what it means distributed across the entire planet, averaged globally, including the poles, the oceans, and every landmass. Individual regions experience far more extreme local deviations, some areas warming 6 to 8 degrees Fahrenheit above their historical averages. The global average blends those extremes with cooler or slower warming regions. The carbon dioxide driving this warming does not spread evenly through the atmosphere and then stop. It accumulates. Carbon dioxide released today stays in the atmosphere for hundreds to thousands of years. The emissions from a coal plant burning 50 years ago are still in the atmosphere right now, still trapping heat. That is why the warming continues, even as conversations about emissions reductions expand. Scientists studying the carbon dioxide record confirmed that the atmospheric system is responding to concentrations that have no modern parallel. The models used to predict warming effects were built on data from a world with lower concentrations. As concentrations push into ranges that have no recent analog, the predictive accuracy of older models decreases. Carbon dioxide was the headline of 2024, but the World Meteorological Organization reported that it arrived with two other gases that were also hitting records of their own. Gases that most people have never thought about and that accelerate the warming system from directions carbon dioxide alone cannot reach. Those gases are the next piece of this story, and they close a loop that makes the whole picture significantly harder to slow down. When scientists talk about greenhouse gases, carbon dioxide gets most of the attention. But the World Meteorological Organization confirmed in 2024 that two other gases, methane and nitrous oxide, also reached all-time high concentrations in the atmosphere that year. Confirmed, both hit their highest recorded levels, and both operate differently than carbon dioxide in ways that make them especially concerning. Methane is a more potent greenhouse gas than carbon dioxide over short time periods. Over 20 years, a given amount of methane traps roughly 80 times more heat than the same amount of carbon dioxide. Confirmed. The reason methane matters so acutely right now is that it degrades in the atmosphere within a decade or two, unlike carbon dioxide, which persists for centuries. That sounds like good news. But it also means that methane levels respond much faster to changes in emission sources. More methane released now produces rapid warming effects within years. Methane comes from multiple sources. Natural gas and oil production leak it during extraction, transportation, and storage. Livestock farming produces it as a byproduct of digestion. Landfills generate it as organic waste decomposes without oxygen. And one source that scientists are watching very carefully: thawing permafrost in the Arctic. Permafrost is ground that has remained frozen for thousands of years across large portions of the Arctic and subarctic regions. Trapped inside that frozen ground is an enormous amount of ancient organic material, dead plants and animals that never fully decomposed because the cold kept them preserved. As the Arctic warms and permafrost thaws, That material starts decomposing. Decomposition releases methane. Scientists confirmed that Arctic permafrost thaw is already contributing methane to the atmosphere, though the exact rate and long-term trajectory remain areas of active research, with some uncertainty. What is confirmed is that the potential methane release from permafrost represents one of the largest carbon stores on Earth, and even a fraction of it becoming active would significantly accelerate warming. Nitrous oxide is the third greenhouse gas that hit a record in 2024. It comes primarily from agricultural practices, specifically from synthetic fertilizers applied to soil, and from industrial processes. Nitrous oxide is roughly 270 times more potent than carbon dioxide as a warming agent over a century. Confirmed. Its atmospheric lifetime is over 100 years. The three gases together, carbon dioxide, methane, and nitrous oxide, form an interlocking system. Carbon dioxide sets the baseline warming. Methane adds rapid, intense heating over short periods. Nitrous oxide adds long-term amplification that persists across generations. All three hitting simultaneous record concentrations in 2024 means the atmosphere is receiving reinforcement from every major greenhouse gas at once. Scientists confirmed the 2024 measurements through multiple independent monitoring networks. The climate system is not responding to one driver, it is responding to all three simultaneously, and each one is reinforcing conditions in different parts of the atmosphere, including the upper atmosphere above the Arctic, where one of the fastest and least understood changes in the climate system is actively unfolding. The Arctic atmosphere is changing in ways that affect every weather pattern across the northern half of the planet. And the specific change happening there right now connects directly to the stalling of the Rossby waves that produced May 18th. The Arctic was never supposed to be humid. For most of recorded history, the air above the polar region has been exceptionally dry. Cold air holds very little water vapor. The combination of freezing temperatures and constant sea ice cover kept the Arctic atmosphere thin, cold, and almost entirely without moisture. That is changing. Scientists confirmed that the Arctic atmosphere is becoming increasingly moist as temperatures in the region rise. Confirmed. The moisture increase is happening at a rate that researchers describe as significant and accelerating. Here is why this matters far beyond the Arctic itself. Moisture in the air changes how heat moves. Dry air does not hold or transfer heat efficiently. Moist air does. When you add water vapor to the Arctic atmosphere, the air becomes more effective at trapping and moving heat. The warming that was already happening because of greenhouse gases gets amplified locally by the moisture that warming created. Moist Arctic air also interacts differently with the ice below it. Sea ice and glacial ice rely on being surrounded by cold, dry air to maintain their surface conditions. When the air above the ice becomes warmer and carries more moisture, it transfers heat to the ice surface more efficiently. Melting accelerates. The ice surface darkens as it melts, absorbing more sunlight instead of reflecting it, which warms the surface more, which warms the air more, which brings in more moisture. This is a local feedback loop operating entirely within the Arctic, stacked on top of the global warming signal from greenhouse gases. Scientists confirmed that sea ice in the Arctic has been declining consistently for decades, with recent years recording summer sea ice extents far below historical averages. The moistening of the Arctic atmosphere also directly influences the jet stream. The jet stream, as established earlier, draws its energy from the temperature contrast between polar air and tropical air. Moist Arctic air is warmer than dry Arctic air. A warmer Arctic means a smaller temperature contrast with the tropics. A smaller contrast means a weaker jet stream. A weaker jet stream produces the slower, more deeply looping Rossby waves that lock weather systems in place for extended periods. The Arctic moisture increase is therefore both a local amplifier and a global disruptor. Locally, it accelerates ice loss. Globally, it degrades the atmospheric circulation that distributes weather patterns across the entire northern hemisphere. NASA's Atmospheric Infrared Sounder, a sensor system launched in 2002 specifically to track moisture distribution in the atmosphere, has been detecting the Arctic moistening trend in its data. Confirmed. The instrument provides global coverage of atmospheric water vapor content at multiple altitudes, making it possible to track changes in the polar moisture profile over time. What the data shows is a trend that has been building for years and has accelerated in the most recent decade. The dry, cold polar air that powered a stable jet stream is being replaced by warmer, moister air that weakens the system piece by piece. The sea ice loss driving that moistening is itself both a product and a cause of the planetary heat imbalance. Every square mile of ice that disappears removes a reflective surface that once bounced sunlight back into space. That absorbed sunlight becomes heat. That heat goes into the ocean and the atmosphere. The ice is not just melting, it is changing the energy accounting of the entire planet. And the planet's energy account, the balance between what comes in from the sun and what escapes back to space, is now running a deficit that scientists describe as the largest in the observed record. That deficit is the next chapter, and the number attached to it has no historical equal. Ice is one of the most powerful climate regulators on the planet, and it works through one of the simplest physical processes imaginable. White surfaces reflect sunlight, dark surfaces absorb it. Fresh snow reflects roughly 80 to 90% of the sunlight that hits it. The ocean absorbs roughly 90% of the sunlight that hits it. Those two numbers sit at opposite ends of the reflectivity scale. Scientists call this property albedo. High albedo means most sunlight bounces back into space. Low albedo means most sunlight becomes heat. When Arctic sea ice covers the ocean surface, the region reflects most of the solar energy hitting it. When that ice melts and exposes open ocean water, the same region flips from a reflector to an absorber. The energy that was leaving the planet now stays inside the climate system. This is confirmed physics. It is not a model projection. It is measurable, observable, and documented by satellite data going back decades. The Arctic has lost more than 2/3 of its summer sea ice volume since the 1980s. Confirmed. That loss represents an enormous change in the planet's reflectivity. Scientists calculated that the additional heat absorbed by the Arctic Ocean surface due to ice loss is comparable to the warming effect produced by roughly 25% of annual global CO2 emissions. That comparison gives scale to what ice loss means in energy terms. The loss does not happen evenly. Ice thins first. Thinner ice breaks apart faster in spring. Breaks expose open water earlier in the season. Earlier open water absorbs heat through more weeks of summer sunlight. That heat delays ice formation in autumn. Later ice formation means the next winter's ice starts thinner. Thinner ice melts faster the following spring. The cycle accelerates itself. Scientists confirmed this self-reinforcing pattern as one of the clearest amplifying feedbacks in the Arctic climate system. The Greenland ice sheet adds another dimension to this picture. Greenland holds enough ice that if it melted completely, global sea levels would rise roughly 20 feet, confirmed. Full melting is a process measured in centuries at current rates, but the rate of ice loss from Greenland has been accelerating. Scientists confirmed that Greenland is losing ice mass faster now than it was 20 years ago. The meltwater runs off into the North Atlantic, adding cold fresh water to a region where ocean circulation patterns are sensitive to salinity changes. That freshwater input connects to a separate system entirely, the large-scale ocean current that moves warm water northward along the Atlantic coast of North America and Europe. Scientists are actively studying whether that current system is slowing down. Evidence exists for slowing, but the extent and timeline remain areas of genuine scientific uncertainty and unknown. What is confirmed is that every piece of ice that melts, whether sea ice or glacial ice, changes the energy balance of the planet in measurable ways. Less reflection, more absorption, more heat in the system. All that absorbed heat has to go somewhere. Most of it goes into the ocean, but a growing portion of it feeds directly into the atmospheric heat imbalance that the World Meteorological Organization described as unprecedented. That imbalance has a specific measurable description: incoming energy versus outgoing energy, and the gap between those two numbers is the clearest single measurement of how far out of balance the planet currently sits. Every second the Sun sends energy toward Earth, sunlight crosses 93 million miles of space and hits the planet. Some of it reflects off clouds and ice back into space. The rest gets absorbed by the land, the ocean, and the atmosphere. Earth then radiates some of that energy back out as heat. The balance between what comes in and what goes out determines the planet's temperature. For most of the past 10,000 years, that balance was roughly stable. Energy in, energy out. Temperature stays within a livable range. Small natural variations shifted the balance slightly, producing ice ages and warmer periods over thousands of years. But the system oscillated within a recognizable range. The World Meteorological Organization confirmed in early 2026 that the planet is more out of balance than at any point in the observed measurement record. Confirmed. Incoming solar energy is now significantly exceeding outgoing energy. The planet is absorbing more than it releases, and the gap is growing. Scientists measure this imbalance using satellite instruments that track the energy arriving from the Sun and the energy leaving the top of the atmosphere. The difference between those two measurements is called Earth's energy imbalance. A positive imbalance means the planet is gaining heat. A negative imbalance means it is losing heat. The current imbalance is positive, and the measured value has been increasing. To picture the scale, consider this: the amount of excess energy currently accumulating in the Earth system every single second is roughly equivalent to the energy released by 4 atomic bombs the size of the one dropped on Hiroshima. Every second, continuously. That energy does not vanish. It goes into the ocean, the atmosphere, the land, and the ice. 90% of it goes into the ocean. The remaining 10% distributes across the land surface, the atmosphere, and the cryosphere, meaning the ice-covered regions of the planet. That 10% outside the ocean is what directly heats the air you breathe, drives the temperature records at surface weather stations, and produces the extremes like the 217-degree gap in March and the stalled Rossby wave in May. 10% of an already enormous energy excess is still an enormous amount of energy. The imbalance grows because greenhouse gases are trapping more of the outgoing heat radiation before it can escape to space. Carbon dioxide, methane, and water vapor intercept that outgoing heat and redirect it back toward the surface. The more of these gases in the atmosphere, the more outgoing heat gets intercepted, and the larger the imbalance becomes. Scientists confirmed that the imbalance has been positive and growing for decades. The most recent measurements show it at levels that exceed historical estimates for any period in the modern climate record. There is no natural mechanism currently operating that would reverse this imbalance in the short term. The gases driving it persist for decades to centuries. The ocean heat they have already caused continues evaporating water vapor that amplifies warming further. The ice loss they have driven continues reducing planetary reflectivity. The accumulation of that imbalance over 11 consecutive years produced something that the World Meteorological Organization documented in its most recent annual report. 11 years of records. 11 years in a row. Every one of them the hottest the planet had ever seen. The World Meteorological Organization released its annual climate assessment in early 2026. The finding at the center of that report was simple and precise. The period from 2015 to 2025 was the hottest 11-year block in the entire observed temperature record. Confirmed. Every single year in that period ranked among the warmest ever measured globally. To understand what 11 consecutive record years means, consider how temperature records normally work. Records get broken occasionally. A particularly strong natural climate event, like the warming of the Pacific Ocean during a powerful natural cycle, can push a year into record territory, but the record usually stands for a while. Other years sit below it. The distribution of warm and cool years spreads across a range. What happened between 2015 and 2025 broke that pattern completely. The record fell every year, or stayed at the new record. The period produced no cool years, no near-average years, no natural variation that pulled temperatures back toward the historical mean. The entire 11-year stretch sat in territory the planet had never recorded before. 2025 sat at the top, the warmest single year in the observed record. Scientists confirmed that the global average surface temperature in 2025 reached 2.57 degrees Fahrenheit above the 1850 pre-industrial baseline. Confirmed. The 1850 baseline matters because it represents conditions before large-scale industrial fossil fuel burning began altering the atmosphere. Every degree of warming above that baseline is warming driven by human activity, layered on top of whatever natural variability the climate would have produced on its own. 2.57 degrees Fahrenheit is 1.43 degrees Celsius above that baseline. Climate agreements like the Paris Agreement set targets around limiting warming to 1.5 degrees Celsius above pre-industrial levels, because scientists identified that threshold as a point beyond which many climate risks escalate significantly. 2025 exceeded it. For a single year to cross that threshold temporarily does not mean the long-term average has crossed it permanently yet. Climate scientists distinguish between a single-year spike and a sustained multi-decade average. The long-term average is still approaching but has not yet crossed 1.5 degrees Celsius for the full period. However, the trajectory of the 11-year block makes the sustained crossing increasingly likely within the coming decade. Scientists confirmed this trajectory assessment. What 11 consecutive record years means in practical terms is that the climate system has shifted its baseline. The new normal is warmer than the old normal. Events that were considered extreme under the old baseline happen more frequently under the new one. The edge of the statistical distribution, where the rare and unprecedented events live, has moved. That shift is precisely why May 18th produced 404 alerts. The atmospheric conditions that made the stalled Rossby wave so destructive were not random. They emerged from an 11-year accumulation of atmospheric changes that pushed temperature readings, moisture levels, and energy imbalances into ranges the old forecasting tools were not calibrated for. The 2.57 degree number sounds abstract, but it has a ground-level translation. A number that describes what 1.43 degrees Celsius above baseline actually feels like when you are standing in it. 2.57 degrees Fahrenheit sounds like a minor adjustment, like turning a thermostat up by less than 3 degrees in your house, small enough to barely notice. Spread across an entire planet, it is catastrophic. The global average temperature is exactly that, an average. It blends readings from the ocean surface covering 70% of the planet, from the poles, from the equator, from the highest mountain peaks, and the lowest desert floors. The average smooths out every local extreme into one number. That smoothing means the global average moves slowly and only shifts meaningfully when something very large is happening across the entire system simultaneously. When the global average moves 2.57 degrees Fahrenheit above the pre-industrial baseline, specific regions have already moved far beyond that, confirmed by surface temperature data from monitoring networks worldwide. The Arctic has warmed by roughly 7 to 10 degrees Fahrenheit above its pre-industrial average in recent decades. Confirmed. Parts of Siberia have recorded winter temperatures 10 to 12 degrees Fahrenheit above their historical averages. Mediterranean regions have experienced summer heat averages 4 to 6 degrees Fahrenheit above historical norms. The American Southwest has seen multi-year drought conditions consistent with a region warming at roughly twice the global average rate. The 2.57 global average is the number produced when those extremes at the high end get blended with regions that have warmed more slowly, like parts of the Southern Ocean and certain areas of the tropics. For a 15-year-old living in the United States, the 2.57-degree shift translates into concrete experiences. More days above 100 degrees Fahrenheit in cities that historically saw only a few per summer, wildfire seasons that now extend across more months of the year than they did a generation ago, winters that arrive later and break earlier, hurricane seasons that produce more storms that rapidly intensify before forecasters can issue adequate warning. Scientists confirmed that heat-related health impacts have increased significantly alongside the temperature rise. The number of days where outdoor heat reaches levels dangerous for human health, particularly for the elderly, children, and people doing physical labor, has grown in recent decades. Confirmed, the agricultural system built around historical growing seasons is also adjusting under the new baseline. Planting windows have shifted. Crop stress events from heat and drought have increased in frequency. Water availability in snowpack-dependent regions, like the western United States, has declined as winter precipitation falls more as rain instead of snow, reducing the natural water storage that snowpack provides. 2.57 degrees Fahrenheit is the summary number for all of those changes combined. It is the single digit that represents 11 years of consecutive heat records, the largest ocean heat content in measured history, the moisture loading of the atmosphere, the weakening of the Arctic temperature gradient, and the stalling of Rossby waves over continents. Every chapter of this story connects to that number, and every chapter connects to why, on May 18, 2026, the historical forecasting models that meteorologists rely on produced predictions that the atmosphere simply ignored. The models failed that day, and the reason they failed says something fundamental about where the science of weather prediction now stands. Every weather forecast you have ever seen came from a model, a set of mathematical equations that describe how the atmosphere behaves. Those equations were built using decades of observation. Scientists recorded temperature, pressure, humidity, wind speed, and dozens of other variables at thousands of locations around the world. They identified patterns, they wrote equations to describe those patterns, and they fed current conditions into those equations to predict future ones. The models work remarkably well under normal conditions. A 7-day forecast today is about as accurate as a 3-day forecast was 30 years ago. The models have improved steadily through better data, faster computers, and refined equations. They are genuinely impressive tools, but they have a fundamental structural limitation. They are calibrated to the past. Every equation in a climate or weather model was derived from historical data. The patterns the model recognizes are patterns that appeared in the historical record. The relationships between variables, the way temperature and pressure interact, the way moisture loading affects storm intensity, all of it is expressed in terms of what happened before. When current conditions stay within the range of what has happened before, the models perform well. When current conditions push beyond that range, the models lose accuracy. They extrapolate from a baseline that no longer describes the system they are trying to predict. On May 18, 2026, temperatures at the altitude meteorologists use to track large-scale air movement reached 2 to 3 standard deviations above the operational climate record. That means the observed conditions landed outside the range on which the model's core equations were calibrated. Confirmed. Meteorologists documented the deviation clearly. Scientists at research institutions studying the event noted that the failure was not a software error or a measurement mistake. The instruments worked perfectly. The models received accurate inputs. The model simply produced outputs that did not match the observed atmospheric behavior, because the atmospheric behavior was outside the range the models were designed to describe. Climate researchers in Nigeria, working independently on local agricultural impacts of climate anomalies, noted that their historical data contained no precedent for the temperature patterns they were seeing. Confirmed. Different continent, same phenomenon. Events consistently exceeding the range of the historical record in every monitoring system that was looking. This is a recognized challenge in climate science called model uncertainty at the extremes. Scientists know that the further conditions drift from the historical baseline, the less reliable model predictions become. They are actively working on next-generation models that incorporate wider ranges and nonlinear responses, meaning responses that do not scale smoothly with inputs, but jump abruptly when systems cross thresholds. Those next-generation models are still in development. In the meantime, the atmosphere is producing events that the current generation of models struggles to characterize accurately. Meteorologists described the forecasting environment on May 18th as operating without a reliable map. They knew the general structure of what was happening. They understood the wave mechanics, the moisture loading, and the temperature extremes. What they could not predict with confidence was the precise evolution of each extreme system, because the models generating those predictions were working with equations built for a different atmosphere. The inability to predict accurately is not just a scientific problem. It is an operational problem with direct consequences for public safety. And that consequence sharpens when you understand what a model failure means for the people who depend on forecasts to make life or death decisions. A tornado warning gives people roughly 13 minutes to reach shelter. A flash flood warning gives emergency managers time to close roads and position rescue teams. A fire weather alert gives incident commanders time to pre-position equipment and issue evacuation orders. A blizzard warning gives transportation agencies time to pre-treat roads and stage plows. Every one of those response windows depends on the forecast being accurate. The warning only works if it comes early enough for people to act. And the forecast only comes early enough if the model predicting the event performs reliably. On May 18th, the models were working at the edge of their reliability range. Confirmed. Temperature readings at altitude exceeded the historical parameters the models used. The evolution of each of the 5 simultaneous extreme systems carried more uncertainty than a standard operational forecast. Forecasters were issuing warnings based on the best available guidance, while knowing that guidance carried higher than normal uncertainty. This is not a hypothetical risk. Forecasters documented the challenge in real time. The National Weather Service meteorologists issuing alerts that day were operating with degraded model confidence on multiple events. What that means in practice is harder warning lead times. A flash flood that the model predicted arriving in 8 hours might arrive in 5. A tornado-producing storm that the model tracked on one path might shift. Fire weather conditions that appeared to be developing over the course of a day might accelerate within a few hours. The uncertainty does not make the forecast useless. It compresses the safety margin. For emergency managers, compressed safety margins translate directly into harder decisions. Do you order a large-scale evacuation based on a forecast carrying high uncertainty, knowing the cost of a false alarm? Or do you wait for greater certainty knowing the window for safe evacuation shrinks every hour? These are real decisions that real people made on May 18th while managing 5 simultaneous emergencies. Scientists and emergency management researchers are actively studying how to improve decision-making frameworks for multi-hazard events under high forecast uncertainty. That work is ongoing. The model limitation is also a long-term planning problem. Infrastructure design, building codes, floodplain maps, and land use regulations all rely on risk assessments built from historical climate data. If the historical data no longer accurately represents the range of events that can occur, then every risk assessment built on that data is potentially underestimating the threat. A 100-year flood standard built from historical precipitation data may now represent a 50-year event or a 30-year event in a warmer, wetter atmosphere, confirmed by multiple studies analyzing how historical flood return periods have shifted. Bridges, levees, storm drains, and emergency protocols calibrated to the old standard are now calibrated to a risk level that the atmosphere has already moved past. Scientists confirm that updating infrastructure standards to match current atmospheric behavior is technically possible, but requires a full recalibration of the historical baseline assumptions underlying every risk model in use. That recalibration is a massive undertaking, and it is happening more slowly than the atmosphere is changing. Meanwhile, the atmosphere keeps generating events that the old frameworks cannot contain. And the mechanism amplifying those events, the feedback loop connecting warming to moisture to more warming, has been running for decades without a break. That loop has a structure. It feeds itself. And understanding exactly how it compounds is the key to understanding why the events of 2026 felt so different from anything the generation before had seen. A feedback loop is a system where the output becomes part of the input. The result of a process feeds back into that same process and changes how it runs. Feedback loops exist everywhere in nature. They can be stabilizing, meaning they push a system back toward equilibrium. Or they can be destabilizing, meaning they push a system further and further from equilibrium. The climate system contains both kinds, and right now, the destabilizing ones are running stronger than the stabilizing ones. Here is the core loop. The atmosphere warms slightly from greenhouse gas emissions. Warmer air holds more water vapor. Water vapor is itself a greenhouse gas. More water vapor traps more heat. Less ice means less sunlight reflected back to space. More absorbed sunlight adds more heat to the ocean and atmosphere. Warmer oceans evaporate more water. More evaporation adds more water vapor. The loop continues. Scientists confirm that this interlocking set of feedbacks is actively amplifying the initial warming signal from carbon dioxide. Confirmed. The warming you see today is larger than the warming that carbon dioxide alone would have produced without these amplifiers running. The water vapor feedback alone, as described earlier, roughly triples the initial carbon dioxide warming effect. The ice albedo feedback, the loss of reflective ice exposing dark ocean and land, adds another significant amplification. The permafrost thaw releasing methane, still being quantified, adds another layer. These feedbacks do not all operate on the same timescale. Water vapor responds almost instantly to temperature changes, within days or weeks. Ice loss operates on years to decades. Permafrost methane release operates on decades to centuries. The short-term feedbacks are already fully engaged. The longer-term feedbacks are beginning to activate. What makes this loop difficult to interrupt is the momentum built into the slower components. Even if every greenhouse gas emission stopped completely today, the water vapor feedback would continue as long as temperatures stay elevated. Temperatures would stay elevated as long as ocean heat continues evaporating moisture into the atmosphere. Ocean heat would continue warming the surface for decades because the heat already stored in the deep ocean has no quick exit path. Scientists estimate that even under an aggressive emissions reduction scenario, some degree of continued warming is locked in for the next several decades due to the heat already accumulated in the ocean system. This does not make emissions reductions pointless, it makes them urgent. Because the difference between aggressive action and continued inaction is the difference between a manageable trajectory and one that pushes feedbacks further toward points where they become harder to influence. Whether any of the active feedbacks are approaching an irreversible threshold is one of the most contested questions in climate science right now. Scientists describe these potential thresholds as tipping points, levels of warming beyond which certain feedback systems accelerate automatically and cannot be reversed on human timescales. The exact location of these thresholds is unknown. Whether any have already been crossed is debated. These are confirmed unknowns. The fire weather events that formed part of May 18th connect to this loop in a specific and visible way. The conditions producing extreme fire weather are not independent of the feedbacks. They are one of the loop's most dramatic visible outputs. And from a satellite, those conditions have a signature you can read from space. Before a wildfire starts, The atmosphere above the region already shows its hand. Weather satellites equipped with infrared and microwave sensors can detect the surface temperature of the land below, the moisture content of the atmosphere above it, and the wind patterns moving through the system. When those three variables combine in a specific configuration, scientists can identify the pre-fire signature hours or even days before a spark appears. Extreme fire weather requires three things: critically low fuel moisture, meaning the vegetation on the ground is dry enough to ignite easily and carry fire rapidly; low atmospheric humidity, meaning the air will not suppress the combustion or slow the fire's spread; high wind speeds, meaning any fire that starts will move faster than suppression crews can track. Satellite data on May 18th showed all three conditions active across the Western Fire Weather Alert Zone. Confirmed. The National Weather Service classified the risk as extreme, the highest tier on the fire weather scale. From orbit, the pre-fire landscape reads as a heat anomaly. Dry soil and vegetation absorb and release heat differently than moist soil. Satellite thermal sensors detect surface temperatures that indicate critically low moisture in the top layer of soil and plant matter. Paired with wind field data showing sustained high speeds and atmospheric readings showing single-digit relative humidity, the pre-fire signature becomes unambiguous. A relative humidity reading below 15% over dry vegetation with wind speeds above 30 miles per hour is a condition fire scientists call red flag. Below 10%, with winds above 40 miles per hour, crosses into extreme territory, where fire behavior becomes extremely difficult to predict and control. Embers can travel more than a mile ahead of the fire front in strong wind conditions, starting new ignitions far outside the active suppression perimeter. Climate science confirmed that the number of days per year meeting red flag criteria has increased across the western United States over the past several decades. Confirmed. Longer, drier summers, reduced snowpack reducing soil moisture through the spring and summer seasons, and stronger wind events tied to shifting pressure patterns have all contributed to a longer and more intense fire weather season. The specific contribution of the stalled Rossby wave on May 18th was the duration of fire weather conditions. A moving weather system brings dangerous conditions and then transitions. A stalled system locks dangerous conditions in place for days. Extreme fire weather that persists for multiple consecutive days is operationally far more dangerous than a single-day event because suppression resources exhaust, crew fatigue accumulates, and the probability that a spark will find conditions to grow into a major fire increases with every additional day the red flag period extends. Satellite monitoring that detected the fire weather signature on May 18th was part of the same observational network tracking the simultaneous tornado outbreak, the flash flood risk, the blizzard, and the heat dome. One planet, one day, every extreme the atmosphere could produce, visible from orbit at the same moment. The flash flooding component of that day had its own satellite signature, and the way that signature has changed over the past decade explains why flash floods now kill and destroy with a speed that emergency managers describe as fundamentally different from anything in the historical record. Flash floods used to build. Water would rise over the course of an hour or two, long enough for people in low-lying areas to see it coming and move. Roads would flood, then become passable again as the storm moved through. The timeline was uncomfortable, but it was readable. That timeline has compressed. Scientists confirmed that rainfall rates during flash flood events have increased significantly in recent decades. Confirmed. The physical reason is the moisture loading described earlier. Warmer air holds more water vapor, and when that moisture-laden air releases its water, it releases more of it in a shorter period. The storm does not last longer. The rain just falls faster while the storm is overhead. A rainfall rate of 2 inches per hour is significant but manageable for most urban drainage systems designed to modern standards. A rainfall rate of 4 inches per hour overwhelms nearly every urban drainage system in the country, including systems built to relatively recent specifications. The difference between those two rates is achievable through the moisture increase the atmosphere has already undergone. On May 18th, the flash flood warming active across parts of the country was tied to atmospheric conditions where moisture content was running well above seasonal norms. A stalled low-pressure system was drawing Gulf of Mexico air northward continuously, reloading the atmosphere above the affected region with warm, humid air each time a rainfall event partially depleted it. The result was a system that produced multiple rounds of heavy rain rather than one passing storm. Multiple rainfall rounds over the same geography are particularly dangerous for two reasons. First, the ground becomes saturated after the first round, meaning subsequent rainfall has nowhere to go but into the drainage system and then into streams and roads. Second, streams that are already running high from earlier rainfall can reach flooding stage much faster from a second rain event than they would from a first. This compounding pattern, called a training thunderstorm event, because successive storms train over the same area, like railroad cars over the same track, is one of the most dangerous flash flood producers in the meteorological toolkit. Stalled atmospheric systems dramatically increase the probability of training events. Scientists confirmed that infrastructure calibrated to handle historical peak rainfall rates is being overwhelmed more frequently. Confirmed, flood damage statistics across the United States show an upward trend in flash flood events, causing major infrastructure failure, meaning road washouts, bridge collapses, and drainage system failures that go beyond surface flooding. The human danger in these events is the speed of water rise. Drowning in a vehicle caught in a flash flood has become one of the leading weather-related causes of death in the United States, precisely because the water rises faster than people expect and faster than historical experience prepared them for, confirmed by National Weather Service mortality data. The flash flood component of May 18th was not an isolated extreme. It was a predictable output of a moisture-loaded atmosphere trapped under a stalled wave over a specific geography. All 5 extremes that day were predictable in that sense. The wave structure was visible, the moisture content was measurable, the temperature anomalies were tracked. What was unpredictable was the precise location, timing, and intensity of each event, because the models generating those specific predictions were operating outside their reliable range. That model limitation runs deeper than a single day's forecast failure. It runs into the structure of the jet stream itself, which is bending in ways at 30,000 feet that are trapping heat over cities in patterns that older observations never captured at this scale. At roughly 30,000 feet above the surface, the jet stream is bending in ways that scientists describe as amplified beyond historical norms. The bends have gotten bigger, they have gotten slower, and they are persisting longer over specific regions. Scientists confirmed that the amplitude of Rossby wave patterns in the Northern Hemisphere jet stream has increased in recent decades. Confirmed. Amplitude means the depth of the bends, how far north and south the jet stream swings as it circles the globe. Bigger swings mean bigger contrasts between adjacent regions, more dramatic cold outbreaks next to more dramatic heat events, more persistent blocking patterns that lock weather in place. The jet stream at 30,000 feet is invisible. You cannot see it, but its position determines almost everything about the weather below it. When the jet stream runs directly over a city, that city sits in a zone of active weather change, temperature swings, shifting winds, and frequent storm passage. When the jet stream bends away from a city and leaves it under a blocking high-pressure system, that city enters a stable, stagnant air mass that can persist for weeks. Blocking high-pressure systems are the atmospheric structures that produce the most extreme sustained heat events. Under a blocking high, the sky stays clear. Sunlight hits the surface day after day without cloud cover to moderate it. Temperatures build. Nighttime temperatures stay elevated because the atmosphere above is too stable to allow the heat to escape efficiently. After a week, you have a heat wave. After 2 weeks, you have a heat emergency. Scientists confirmed that blocking events, where the jet stream locks into a position that prevents normal weather progression, have become more frequent and longer lasting in the Northern Hemisphere over the past several decades. Confirmed. The physical link between Arctic warming, jet stream weakening, and increased blocking frequency is established, though the exact magnitude of that link is still being quantified. For cities, the consequence of more persistent blocking is more days of extreme heat per event. A heat wave that would have lasted 4 days under a faster-moving jet stream now lasts 10 or 12. The cumulative heat exposure during a 12-day heat wave is dramatically more dangerous than a 4-day one, because the human body, emergency services, power grids, and water systems all have limited capacity to sustain performance under heat stress for extended periods. Power demand during heat waves has broken records in multiple cities in recent years, as air conditioning use surges simultaneously across entire regions. Grids designed for historical peak demand face conditions that exceed those design parameters. Confirmed. Infrastructure failures during heat waves have killed people by cutting power to homes and facilities that relied on cooling to keep vulnerable individuals alive. The jet stream stress is not just a weather phenomenon. It is an infrastructure stress test, happening repeatedly and with increasing frequency. Scientists who study the jet stream noted that its behavior is now a research priority, because the atmospheric river that was once predictable and stable has become variable in ways that strain every forecast system built to track it. The ancient atmospheric record, including what coral reefs preserved about past heat events, is now one of the tools scientists are using to understand whether what the jet stream is doing now has any historical parallel. The answer from that ancient record is both illuminating and unsettling. Coral reefs are alive. They grow in thin layers, year after year, building their calcium carbonate skeletons at rates tied to water temperature, chemistry, and light. Each layer is a record, a physical archive of the conditions the ocean held at the time that layer formed. Scientists drill cores from coral skeletons, the way they drill cores from ice sheets. They extract a column of material going back decades or centuries. Each layer holds chemical signatures that tell researchers the temperature of the water when it formed, how acidic the ocean was, and how much oxygen was dissolved in the surrounding water. Confirmed. Coral records have been used to reconstruct ocean temperatures going back several hundred years in regions where no human instruments existed. What the coral records show for the past several decades is a warming trend that runs faster than any natural variability in the historical archive. Confirmed. Scientists comparing modern coral temperature records to pre-industrial sections of the same cores found that recent warming in tropical ocean regions exceeded anything the corals had recorded during natural climate variations. Over the past several centuries, the reefs themselves are suffering directly. Ocean warming causes coral bleaching, a process where heat-stressed corals expel the algae living in their tissues. Those algae provide the coral with most of its food through photosynthesis. Without them, the coral turns white and begins starving. If water temperatures return to normal quickly enough, the coral can recover. If elevated temperatures persist, the coral dies. Scientists confirm that mass coral bleaching events, affecting large sections of reef systems simultaneously, have increased dramatically in frequency since the 1980s. Events that occurred once per decade now occur multiple times per decade. The Great Barrier Reef experienced mass bleaching events in 2016, 2017, 2022, and again in recent years. Confirmed. The frequency left insufficient time between events for full recovery. Beyond their ecological role, coral reefs protect coastlines. They absorb wave energy and reduce erosion. Coastal communities in tropical regions rely on the reef buffer to protect shorelines from storm surge. A dead reef does not provide that buffer. As reefs degrade, the coastlines behind them become more vulnerable to the intensified storms that the warming ocean simultaneously produces. The coral record extending back through natural climate variability gives scientists a baseline for how much ocean temperatures have changed in the past without human influence. That baseline makes the current rate of change stand out sharply. Natural temperature variations in the tropics over the past several centuries were measured in fractions of a degree. Current warming in those same regions has reached multiple degrees within decades. The ice core record from the Antarctic, the coral records from tropical oceans, and the instrumental temperature record from global weather stations all tell the same story from different angles. The current rate and magnitude of change sits outside the range of natural variability in every archive scientists have found. Scientists looking for a natural parallel to the current atmospheric state have had to reach back millions of years to periods of geological time that predate human existence to find conditions that match what instruments are recording now. That reach into deep time connects directly to a space mission that discovered something unexpected, something that involved Mars, a solar storm, and a compressed atmosphere, and what it suggested about what happens to planets when their atmospheric protection starts to change. In 2023, a spacecraft orbiting Mars detected something unusual during a solar storm. The storm sent a burst of charged particles and radiation toward the planet, and the spacecraft, called the Mars Atmosphere and Volatile Evolution Mission, detected the first confirmed instance of a phenomenon called the Schwann-Wolf effect deep within the Martian atmosphere. Confirmed. The Schwann-Wolf effect describes a specific distortion of the magnetic field environment around a planet during intense solar activity. On Mars, which lacks the protective global magnetic field that Earth possesses, the interaction between the solar storm and the upper atmosphere compressed layers of the Martian atmosphere inward and altered their structure temporarily. Mars is a planet that lost most of its atmosphere billions of years ago. Scientists believe Mars once had a thicker atmosphere, liquid water on its surface, and conditions that may have supported some form of microbial life. The mechanisms behind its atmospheric loss are still being studied. One confirmed factor is that without a strong global magnetic field, Mars had no shield against solar wind, the constant stream of charged particles the Sun produces. Over billions of years, that solar wind gradually stripped away the Martian atmosphere. Earth has a global magnetic field. It deflects solar wind and protects the atmosphere from the same stripping process that may have contributed to Mars losing its air. That protection has kept Earth's atmosphere intact through billions of years and multiple periods of dramatic climate change. Scientists who study Earth's upper atmosphere use data from Mars and other planets to understand atmospheric physics in environments where conditions differ from Earth's. The detection of the Schwann-Wolf effect on Mars was significant because it confirmed that even temporary solar events can alter atmospheric structure on planets with weak magnetic shielding. On Earth, the relevance is different. Scientists are not suggesting Earth faces the same atmospheric loss as Mars. Earth's magnetic field remains robust. The comparison is more subtle. As Earth's atmosphere changes its composition and thermal structure due to greenhouse gas loading, the behavior of the upper atmosphere changes too. The layers that interact with solar radiation behave differently at higher temperatures and different chemical concentrations. Scientists track upper atmospheric temperature changes on Earth using instruments like the atmospheric infrared sounder. The long-term behavior of the upper atmosphere under current greenhouse gas concentrations is an active area of research. Some changes at high altitudes remain poorly understood or untracked by existing baseline models. Confirmed unknown. The Mars data point is a reminder that atmospheric systems are not permanent by default. They are maintained by ongoing physical and chemical processes. Change those processes significantly enough, and the atmosphere changes too. The question for Earth is not whether the atmosphere will disappear. The magnetic field prevents that. The question is how the atmosphere will redistribute heat, how its circulation patterns will shift, and how those shifts will express themselves in the extreme weather events that communities on the surface have to live through. Climate models are the primary tool for answering that question, and the gap between what those models predicted decades ago and what has actually happened is a measurement of how much the atmosphere has already moved. In the 1980s and 90s, climate scientists ran the first generation of global climate models. These early models took known physics, the behavior of greenhouse gases, the way the ocean absorbs heat, the role of ice in reflecting sunlight, and projected forward. They predicted that adding more carbon dioxide to the atmosphere would warm the planet, shift precipitation patterns, intensify storms, and reduce Arctic sea ice. Those predictions were made decades before the events described in this series of chapters. They were made before the 11-year heat record streak, before the 217-degree temperature gap. Before May 18th, scientists confirmed that the broad direction of those early predictions was accurate. The planet warmed, sea ice declined, precipitation patterns shifted, storm intensity increased in measured ways across multiple storm categories. Confirmed, the physics was right. What the early models got wrong was the pace. Several key indicators of climate change have moved faster than the models projected. Arctic sea ice loss has exceeded model projections consistently. Sea level rise has tracked at the higher end of or above projected ranges. Extreme weather event frequency has increased faster than model central estimates predicted for this point in time, confirmed by comparison studies that tracked model projections against observational data. The models also underestimated some feedback mechanisms. The water vapor amplification, while included in early models, was harder to parameterize accurately with the computing power available at the time. The albedo feedback from sea ice loss was included but underestimated in many early model runs. Permafrost methane release was largely absent from early projections. As computing power grew and observational data improved, models became more accurate. Each successive generation of models better captured the feedbacks and produced projections that more closely matched observed outcomes. The current generation of models is significantly more sophisticated than those from the 1980s. But even current models face the structural challenge described earlier. They are calibrated to historical data. The faster the climate moves beyond historical ranges, the larger the uncertainty in model projections at the extremes. Scientists use the range of projections from multiple models run under multiple scenarios to characterize this uncertainty. The range gives policymakers and engineers a spread of possible futures to plan for. Planning for the upper end of that range means building for conditions more extreme than the model's central estimate. Planning for the lower end means building for conditions that observations suggest may already be behind us. The gap between what models predicted and what happened is not a failure of science. It is a measurement of how complex the climate system is and how difficult it is to capture every feedback accurately. The models gave humanity decades of warning. The warning was scientifically valid. The question of whether that warning was acted on sufficiently is outside the domain of atmospheric science. What is inside that domain is the confirmation that the atmosphere has moved, that the move has been faster than expected in key areas, and that the atmosphere is now operating in a state where scientists face genuine, documented unknowns about what happens next. Those unknowns have a specific shape. They cluster around a single question that atmospheric scientists return to constantly. How much more can the system absorb before something irreversible happens? There are things scientists know about the climate system with high confidence. Carbon dioxide traps heat. More carbon dioxide means more warming. Warmer air holds more moisture. Ice reflects sunlight and its loss adds heat to the ocean. These are confirmed. The physical laws are solid. There are things scientists know with moderate confidence. The 11-year heat record streak reflects a genuine shift in the climate baseline. Rossby wave behavior has changed as the Arctic warms. Extreme weather events are increasing in frequency and intensity. These are well supported by data across multiple independent observational systems. And there are things scientists genuinely do not know. How close the climate system is to crossing thresholds where feedbacks become self-sustaining and irreversible. These are confirmed unknowns. Climate scientists call these potential thresholds tipping points. The concept is straightforward. Some systems have a structure where change is gradual up to a certain point, and then abrupt beyond it. A gradually sloping hill is easy to walk down. A cliff edge is a different situation entirely. The question is whether the climate system has cliffs, and how close the current trajectory is to reaching them. Scientists have identified several potential tipping elements in the climate system: the Greenland ice sheet, the West Antarctic ice sheet, the Amazon rainforest, the Atlantic Ocean circulation system, permafrost thaw, coral reef systems. Each of these, if pushed past a specific threshold, could shift rapidly into a new state that would persist even if atmospheric greenhouse gas concentrations were subsequently reduced. The exact temperature or greenhouse gas concentration at which each potential tipping point activates is not confirmed. This is a genuine scientific uncertainty, not a political one. The systems are complex, they interact with each other, and the data on their historical behavior at the relevant thresholds is limited because those thresholds have not been crossed in human history. What scientists can say with increasing confidence is that several of these systems are showing signs of stress consistent with approaching their instability thresholds. Greenland ice loss is accelerating. Amazon drought and fire events have increased in frequency. Atlantic circulation has shown slowdown indicators. Confirmed each of these as trends. The question of how close each is to a tipping threshold remains open. Scientists also confirmed that the thresholds for different tipping elements may be lower than previously estimated in some cases. Research published over the past several years has progressively revised some tipping point estimates downward, meaning they may activate at lower temperatures than earlier projections suggested, confirmed by multiple peer-reviewed studies. The practical implication is that the safety margin for avoiding irreversible change may be smaller than the earlier generation of climate projections indicated. The range of uncertainty is large enough that scientific caution is warranted in both directions. The thresholds may be farther away than current signs suggest, or they may be closer. What happens in the atmosphere after the historical data stops being a guide, after the models lose their calibration anchor, is a question that scientists are actively working to answer. The answer requires new tools, new data, and new frameworks. And it requires being honest about what the next decade of atmospheric behavior will look like, based on the confirmed trajectory, the active theories, and the things that remain genuinely unknown. On May 18, 2026, the operational weather record had no framework for what it was measuring. The model was outside its calibration range. The temperature deviation exceeded the statistical category the forecasting system was built to describe. That is a specific moment in a longer process. The records are not stopping, they are being replaced, one, by new records that will themselves be exceeded. The historical baseline is not disappearing. It is becoming less useful as the gap between past conditions and present conditions grows. Scientists working on next-generation climate models are trying to build tools that do not depend as heavily on historical data as their current frameworks do. Instead of asking what has happened in the past and projecting that forward, they are working toward models that run directly from physical principles, simulating the behavior of the atmosphere from its fundamental physics rather than from its statistical history. These physics-based approaches can, in theory, produce useful predictions even in conditions that have no historical analog. They do not need the past to have seen something in order to simulate it. But building and validating them requires enormous computing resources and observational data to test against. Both are actively being developed. In the meantime, meteorologists are adapting their workflows. Ensemble forecasting, where multiple model runs are generated with slightly different starting conditions to capture uncertainty, has become more important. Forecasters now communicate uncertainty ranges more explicitly in their public guidance. Emergency managers are learning to build response plans that can activate across a range of possible scenarios rather than planning for a single predicted outcome. Scientists confirmed that the frequency of events reaching the outer edge of the statistical range is increasing. Confirmed. The data shows more events landing in the rare categories, more daily temperature records broken, more rainfall events exceeding historical extremes. The distribution of outcomes is shifting, and the tail of extreme events is getting heavier. This tail fattening effect is one of the most significant and least discussed aspects of climate change at the public level. A 1-degree shift in the average temperature does not just make average days warmer, it shifts the entire distribution of possible outcomes, including the extremes at the far end. A distribution that previously produced an extreme event once per 50 years might now produce it once per 15 years. The average shifted a little. The extreme event frequency shifted dramatically. For the people living through events like May 18th, the tail is where all the danger lives. A tornado outbreak, a heat dome, a flash flood, a blizzard, and an extreme fire weather event all at once is a tail event. It used to be so rare as to be essentially outside planning scenarios. It is now confirmed to have happened. What the next generation of events will look like is where confirmed science gives way to active research, open debate, and genuine uncertainty. The trajectory is established, the feedbacks are running, the threshold questions remain open, and the atmospheric system is generating data that scientists are working to interpret faster than the events themselves are occurring. The atmosphere that produced May 18th is not the end point of a process. It is a data point along a continuing trajectory. Where that trajectory leads over the next decade depends on factors both inside and outside the climate system. The final piece of this story is the one that describes that trajectory as honestly as current science can. What is confirmed for the years ahead, what scientists believe but cannot yet prove, and what remains for now genuinely unknown. The next 10 years of atmospheric behavior are not a mystery. They have a confirmed direction, several active theories, and a set of genuinely open questions. Understanding which is which matters, because the atmosphere does not wait for clarity before producing events. Here is what is confirmed. The greenhouse gases already in the atmosphere will continue trapping heat for decades, regardless of any near-term changes in emissions. The ocean heat already accumulated will continue warming the atmosphere through evaporation and heat transfer. The Arctic will continue warming faster than the global average, and Rossby wave behavior will continue to be affected by the shrinking temperature gradient between the poles and the tropics. Extreme weather events will continue to fall more frequently in the outer edge of the statistical range, confirmed by every major scientific organization tracking these indicators. Global average temperatures will continue rising over the next decade under all realistic emission scenarios. The difference between scenarios is the rate of rise and the peak temperature reached. Confirmed. Emission levels over the next 10 years will significantly determine whether the planet approaches 2 degrees Celsius above pre-industrial levels by mid-century or exceeds it earlier. The infrastructure challenge is confirmed and growing. Every year, the atmosphere continues loading additional moisture. Every year, the heat season extends. The gap between what infrastructure was designed to handle and what the atmosphere can now produce widens. Confirmed by engineering and hydrology research across multiple continents. Here is what scientists believe, but are still confirming. The stalling of Rossby waves and blocking events will likely become more frequent as Arctic amplification continues. Multi-hazard events, where a single atmospheric driver produces several simultaneous extremes across a continent, may become more common as the energy imbalance in the atmosphere grows. Hurricane rapid intensification events, where storms jump dramatically in strength in short windows, will likely occur more frequently over warming ocean surfaces. Here is what remains genuinely unknown: whether any tipping element in the climate system will cross its threshold in the next decade, the precise rate at which permafrost methane release will accelerate as Arctic warming continues, how Atlantic Ocean circulation will respond to the continued influx of cold fresh water from Greenland ice melt, how quickly clouds will change their distribution and properties in a warmer atmosphere, and whether those changes will amplify or partially offset warming. The cloud question is one of the largest remaining uncertainties in climate science. Clouds both trap heat and reflect sunlight. Their net effect depends on their altitude, thickness, and geographic distribution, all of which change as the atmosphere warms. Models disagree on how clouds will respond at higher temperature levels. This disagreement is a genuine scientific uncertainty with significant implications for the overall warming trajectory. For a 15-year-old listening to this in 2026, the next 10 years will be the formative decade of the climate system you will live in for the rest of your life. The events of that decade, the records broken, the thresholds approached or crossed, the infrastructure that holds or fails, will shape the atmosphere for the 50 years after. The atmosphere that produced May 18th is the atmosphere you inherited. The atmosphere of 2036 is the one being built right now, by the feedbacks already running. The decisions being made about energy systems, land use, and infrastructure investment, and the confirmed physics of a planet that is still absorbing more energy than it releases. Scientists are watching every variable. The satellites are running, the instruments are measuring, and the atmosphere, which has already done things that had never been recorded, is not finished showing what it can do.